Welcome to the Natural Language Processing Learn from Scratch lecture series. I'm Sarvesh Subhash. I'll be your instructor for this lecture series. And now we are seeing the second part. Before going to the second part of this NLP pipeline topic based lecture 2, we'll look into what we saw in the first part of lecture 2. So we went through the whole phases, each and every phase on a brief in the NLP pipeline. And then we saw the first phase, that is data acquisition phase, in detail, along with even the implementation. So I request you one thing. Throughout this course, wherever I give some implementations, implement those along with me. Fine. So even in this video and the previous video, I had a lot of implementations for data augmentation, data labeling, and then several things, right? Text extraction using beautiful soup, text extraction from PDF, text extraction from images. So implement all of those and make sure that you have some hands-on practice. Experiment with them on your own as well. Fine, along with my implementation. Fine. So after doing that, after completing that, you can actually come to this second lecture. So here we'll look on to this other processes. So we'll have implementations for pre-processing again, so which we'll be seeing in this lecture in detail. And the feature engineering and modeling will not have that much implementations in this chapter, but then we'll have it in our future lecture series. Fine. So this chapter means this lecture. Fine. So in this lecture, second part, we'll look into pre-processing and the other different phases in detail, but then the implementation will be specifically done for pre-processing because there are a lot of techniques in pre-processing itself. Fine. So yes, now we'll move into the theory part or the briefing on what is this pre-processing. So I told you already that you have to make the NLP systems understand language, right? So what do we do then? We numericalize the text. So, but then all of the text extracted from these different documents, like the PDF or the images or the web pages using Beautiful Soup, all of these are in the form of continuous text. So all of them are continuous paragraphs of text, right? They're just a collection of strings. That is always understood by the computer. But then how do we make the computer understand each and every word properly? So we have to, what do we do for a kid if he has to eat food? We give him bit by bit, right? In a smaller portion, the same process we follow for even the computers. So here we take the whole paragraph of the text fully as a paragraph, and then we sentence tokenize them. So we break them down into sentence by sentence. Fine, with each and every full stop. So we break them down to sentence and sentence, and then we even further. In some cases, we even tokenize the sentence as well into words, and then we process all of these things. Like we lowercase before getting into the words, we first of all do this lowercasing. So we there will be all kinds of letters in the text string, right? Whichever is extracted from the website or the PDF or any document. So for all of these different types or combinations of strings, we need to make them uniform into a lowercase so that it's more easier for us to process. Fine. So we first of all lowercase all of the text, and then we remove certain symbols or the punctuation marks like full stop, comma, all of that, apostrophe, and all of these kind of different symbols. We take out that. These are actually special characters called as punctuation marks, and we remove those. And then we remove even the stop words like in, at, on, the, all of these kind of articles of in English language. So we remove all of that, and then we process. We go through the phase of stemming. The stemming is I'll detail you in brief, in depth in the further lecture series. But then let's just have a brief on what this is. Fine. Stemming is a process where we just remove certain parts of the words to get the root word alone, and then in the lemmatization process, we get the meaningful root word of this root. Fine. So that's lemmatization. So with this, you'll get the token, properly cleaned token or pre-processed token you get. And this one again will be converted into a vector form. And that is how you get the number representation of the words for each and every word in the whole text. And for each and every sentence's word, it will be converted into a number or a token. Token would be converted into a number, and that would be used for processing, right? So So what are we doing now? We are just preparing the data set for getting fed by the model. So this is why it's called pre-processing. Before processing the whole text with the numericals, we're just pre-processing it, cleaning it, and then making sure that the words are in the good form for the model to get input as. Fine. So this is the whole process. So there are several, I told you a lot of different techniques, right? First of all, with even sentence tokenization and then word tokenization and then removing the punctuation marks. All of these different techniques, all of this could be classified as pre-processing. Straightforward. Fine. So that is it. So these are the basic pre-processing techniques. Okay. So there are several procedures under step pre-processing. I've told you everything, almost everything, every single process till now. I've mentioned you in brief on what are these, but then we have grouped different processes together for our own understanding. Fine. So that these are the different groups of steps that we have. So first one is the preliminaries. Preliminaries are group of techniques that are fundamental for any NLP task. Fine. So we start off with sentence segmentation, and then we go with word tokenization. These are the preliminary group of steps, right? And then we have the frequent steps. So all of these different techniques which are frequently done for NLP system for pre-processing is called as frequent steps. Literally, it is that is the meaning. Yes. So all of these stop word removal. Stop word is the in at all of that. I'll give you an example. Fine. We'll see each and everything in detail now. Numberization, removing digits, punctuation, lowercasing. And then we have other steps as well. Normalization, language detection, code mixing, transliteration. So I'll give you briefing on these things as well. And then we have advanced processes like part of sentence. This POS means part of sentence, like noun, adjective. All of these are parts of sentences, right? So POS tagging and then parsing and then conference resolution, etc. So all of these different techniques come under different groups of steps, and we'll look into each and every step in detail. Fine. Okay. So first we have the preliminaries. So what we have here in the preliminaries, we have sentence segmentation. So it can break text at full stops and question marks, but abbreviations and ellipses complicate this. Yes. Unfortunately, most libraries like NLTK handle sentence and word splitting for us. So this is how I told you, right? With each and every sentence. So how will I identify a sentence? We will identify a sentence using the full stop or the question mark or exclamation mark or any kind of sentence stopping punctuation marks. So that would be used as our identifier to segment different sentences. So we get the sentences out of the whole text. Fine. So this is an example. So NLTK is the library that we use for most of the NLP tasks, right? So, and in the previously also we even used NLTK for downloading WordNet in the first part of the second lecture. Why did we use WordNet? We used it for synonym replacement in data augmentation. Remember, in NLP org, everything is connected. So here we use the same NLTK to get this particular function called sentence tokenizer or sent tokenize. Send tokenize and word tokenize. These are two functions that tokenize. Very much straightforward. Tokenize the sentence and tokenize the word. Fine. So here is an example of how it does. So we can directly give the text into this function as a parameter, and then you'll get the output sentence. This function will return the sentences as a list. Fine. And that is all. So this is very much straightforward. Fine. And then you have the word tokenization. So all of these sentences, right? So you have these different sentences are here. My sentences, I'll just go through the code here. So for sentence in my sentences, for each and every element in this array or this list, it returns a list of sentences, right? So we get the list of sentences and then we parse through using the for loop for each and every sentence. And then we first print the sentence and then use this word tokenize for getting the tokens of this sentence itself, word tokens of the sentence. So this is an example. In the previous chapter, we saw so this is actually a sentence that we gave in. that is there in this my sentences, it comes from this paragraph in the previous chapter, from here till this. Fine. In everyday life, is it so? Okay, wait a minute. Okay, it is some sentence, some random sentence that we got into this particular word tokenize, and we got these as tokens. So it gives, even the word tokenize gives a list of different tokens of words or groups of the words itself, right? As a separate string element in a list. So this is how the tokens are made. So this is the word tokenize. So it's very much straightforward. Now what do we do? Now we can actually see this as a visual representation of how it works. So it goes string by string, gets each and every word separated, and then uses them as a separate string, and then that is how you get the tokens. Fine. All of the models, including the LLMs, large language models, or the deep-sea carbons, or the reasoning models, every single advanced model that is out there in the market uses this particular fundamental principle for calculating the words, or calculating or processing the input that you're giving in. Fine. So this fundamental. So it gets into different word groups, word elements in a list, and then these are actually saved, and then these are actually stored, and then these are used as an input for the further processes. What are the further processes? We saw it here. Frequent steps. So we remove all of the words. So we'll see that now. See. Next is the frequent steps. So here what do? We take all of these are the examples of, there are not just these stop words. No, there are a lot more stop words. I'm just giving you an example of a glimpse of how like a common stop word here, but then there are a lot more of them. Fine. So we remove these kind of words because these don't actually give us a meaningful context for the language, right? That is why we remove them. But then in many other cases, like for example, when you're training a large language model, usually we don't remove the stop words. But for smaller NLP models, like the machine learning models or the deep learning models, which are smaller, for them we don't usually input them, or we don't include the stop words. We remove them totally. Only will send the important words. For what? For the machine learning models and the basic deep learning models. But then for the large language models, you will have to sometimes give all of these stop words, because even these stop words, though it is negligible now, but for longer sentences and for longer paragraphs, these stop words could actually convey some kind of meaning which the system might miss out if it's removed. Fine. So for the large language models, when you're training them, you usually give even the stop words also as an input. But then for smaller NLP systems, like using a machine learning or deep learning, basic deep learning models, we don't usually have the stop words. We remove them. Fine. So this is the whole example. So what do we do here? We get in the stop words. See again, observe this carefully. NLTK had both the word net in it, and even it has the stop word stored in it. So this library is very much comprehensive. It has the corpus that is needed for us to process easily. Fine. So thanks to the authors of this library, they have done a impactful work, and it's even used now in many of the industry's basic NLP systems. Fine. So these are the stop words. We remove them directly. So it's very much straightforward. You can see here. So is this actually a function for pre-processing the corpus? And then we define as a function for remove stops digits, and then it's very much straightforward. We use if condition and along with the for loop for removing the stop words from the whole list of tokens, or list of word elements in the list. That is the output of word tokenized function. So this function returns this particular list, right? This list has different words as its element, and this list is actually used as an input here, and you get this. This token is actually the list that you saw there, and all of this processing actually happens. Fine. So this is how you remove the stop words, and then we have to perform the other frequent steps, that is stemming and lemmatization. So this is exactly what it is. Stemming is the process of removing suffixes from words to reduce them to their base form so that the variants such as car, cars, car-like, find all these kind of different derived words could be cut down to their short stem words or the root words. Fine. They might not represent the same meaning, but then we're just removing the suffixes alone. If you remove the suffixes alone, it will become the stem. But then if you want a meaningful representation of the same stem word, then that is where the lemma comes into play. Fine. So here we just remove the suffixes and then we get the word alone. Now, in lemmatization is the process of mapping all different forms of a word to its base word. So, mapping all different forms of the word, meaning running or ran. So, you have ran, run, or these two different tense-based words, but then they represent the same word. So, for both of these run and ran, we come up with the same lemma, that is run. So, that is how you do this. So, we map all of the different forms of the word to its base word or lemma. While this seems close to the definition of stemming, they are in fact very much different. Yes, like how I told you. So, for example, this a particular adjective is there, better. When stemmed, it remains the same. It becomes better itself. But then, if you do this lemmatization, this better becomes good. That is the meaningful form of this word, right? Good, better, best. So that is how it understands. So this is how lemmatization works. So that is the main difference between stemming and lemmatization. Okay, we'll look into it in detail as well, along with the implementation. So again, I told you, NLTK has even the stemmer function in it under the porter class. So you have this, you have to import it from the NLTK stem.porter, import porter stemmer. And then this stemmer stems the words, and then you get this is how you call the function stem. And then you get the output of the words, output of the function as a stemmed word. Fine. So this is an example of stemming. So adjustable could be stemmed into adjust. Formality would be formality. It's very much, are you understanding this? This is without meaning. We just remove the suffixes. That is all it considers. Like stemmer is very much straightforward. It removes the suffix alone. But then lemmatization takes in the words and then gives out the more meaningful root word for that particular word. So I told you, right? Better will become good. Meeting will be retained as meeting. Was will be converted to be. Fine. So this is the lemmatization process and the stemming process is referring between each other. This is how they're different. And then how do you implement the lemmatizer? You have this porter stemmer, and then you have the wordnet based lemmatizer. See, I told you why wordnet is used. Wordnet literally makes it's actually a knowledge base which has connections or relationships also embedded in it, right? Relationship between the words. It's not just a dictionary. Word network is not just a dictionary. It has even the connection between two different words stored in it, like how we saw in the first lecture. And that is why we are using wordnet based lemmatizer, because we need meaningful forms of a word, meaningful short forms of a word. Fine. So here is how we use it. So lemmatizer, we just initiate the wordnet lemmatizer constructor, and then from the constructor you call this lemmatize function, and you get the correct. You get the answer properly. So for this, it will become good. It will be printing us good. That is all. Fine. So it's very much straightforward. And here you can give the what is this part of speech tagging is adjective, as A is adjective. Fine. So this is actually a parameter inside lemmatize. So you have to go through the documentation of lemmatize to understand different parameters that lemmatize function has under this lemmatizer constructor inside this nltk.stem package, right? So go through that. And there's one more library which I have to definitely talk about and even brief you about, and we'll even have the implementation. For all of these different techniques that I've told you till now, we'll have even the implementation properly. Fine. So we have another library, a famous library that is used even by the industry called as spacy, right? So spacy is similar to NLTK, but then it has an additional it has additional features which make it perform better for specific tasks and all. Fine. So for word remove, it loads in its own collection of stop words, and then we actually use it for removing. And then for tokenize, so these are actually different uh, ways of how we process the same thing. There are several libraries, even other than spacy and nltk, there are several other libraries for nlp systems. But then I'm showing you the basic one along with the state of the art ones, so that you have an understanding from the start till the industry standard tools for each and every process, or each and every technique that is used in this pre-processing technique procedure. Now that we have seen all of the processes like lemmatization using NLTK library and the spacy library, we look into the next steps, next procedure, that is the next group of steps we have, that is the other pre-processing steps. So it includes all of the text normalization, language detection, and then code mixing and transliteration. Fine. What is this text normalization? So in text normalization, it's very much straightforward, right? So the we understand that the text corpus, or the collection of data sources that we have or that we rely upon, could have varied number of characters in it. It could have a capital letter, it could have a small letter, it could have numbers, digits, and all of these, right? So all of these different characters or strings in this particular document could be converted into a standard form of text. And for example, if it is a capital letter, we convert it into a lowercase, we convert all of the uppercase into lowercase, and then we convert all of the numbers or digits into the corresponding words. And then we even expand the abbreviations, we expand the short forms, and make all of these different pre-processing steps, right? And we perform this using spacy. So spacy also spacy is specifically used for this kind of normalization. Fine. So this is one technique. And then we have the language detection. So most of you would have identified or realized this in your experience. So many of the text or comments or feedbacks or reviews, whichever is there in the internet, could be having multiple language in the same sentence itself. It could be like a sentence with one word in english, other word in some native language, and the next word in english. So it could be a mixture of those. So, and even the script could also be of a different language, right? So all of these are challenges when it comes to text, and making machines or softwares understand these words or this text and all. So what do? We detect these languages, and then we translate them. So how do we detect these languages? We use a library called Polyglot. Polyglot is a library that is used for detecting the languages and then translating them. Fine. So this is one of the process. And then we have something called as code mixing and transliteration. So code mixing could be, it actually specifically refers to using two different languages, or two different languages between the sentence itself. So like how I told you, in the polyglot, what we saw, the language detection, we just detect the language, but then the detected language script could be of different type. It could not be the same English. But here we have the same script, like the letters would be of English, but then the actual words pronunciation or the meaning could be from a different language. So it could be a transliterated or code mixed sentence, right? I'll give you an example here. This is a phrase from Singlish, right? Singlish is actually spoken in the Southeast Asian countries like the Indonesia or Singapore, all of these. So in all of these places, they mix English with their own native tongue. It could be Tamil, or it could be Mandarin, or Cantonese, or Malay, or Hokkien, or Hakka. So all of these different languages, they transliterate or pronounce or write these all languages in English itself. So they'll transliterate it, and these and within a sentence itself, there could be many languages text. So this is actually an exact proper example. So how this is, right? So this is a real life data set. Like they are really finding these kind of text in the comment sections or some other text corpus, right? So this needs to be addressed, So this is one challenge. So we use this polyglot and many other techniques like Google Translator, or many other open source language translating or translated language translating tools. Fine. So all of these tools could be used to convert these different language based English sentences in either into English or into any specific language that is needed for this particular system, for the particular NLP system. Fine. So this is what is done. So this is one of the pre-processing steps. So it is very much system specific. So there are a lot of varieties. There are a lot of different challenges for different requirements, and these are the different challenges for different requirements itself. Fine. So this is the whole group of steps called other pre-processing steps. These aren't specifically used on a day-to-day basis for pre-processing, but then these are special cases. This could be, but the text normalization could be used on a more common ground. Like it could be used for many of the NLP systems pre-processing step, but then others like the code mixing, transliteration, language detection, these kind of steps could be very much system specific or very much requirement specific. Fine. So these are the whole steps. Fine. Now we move on to the advanced processing. Fine. So in advanced processing, we have POS tagging. So part of speech tagging is a process that we specifically use for NER or name entity recognition kind of NLP systems, or we could even use POS for summarization or heuristic or machine learning based summarization. So all of these different techniques which are machine learning related may depend upon this POS tagging or this part of speech tagging. Fine. So what is this part of speech tagging? It is very much simple. So we know that the sentence is composed of lot of different types of words in grammar, like the adjective, the noun, the verb, and all of these. So all of these could become the different parts of the words, right? Parts of the sentences, and these would be given a tag, right? So with and this the whole POS tag is actually useful for many of the different applications out there, right? I'll give you an example. For example, say you're a bank. Fine. So you have a lot of your organization, like you're a big international bank. Fine. So you are even providing loans to private companies. So you might have more than 1 billion documents, and you might have to find out different names of the organizations and even identify the point of contact for that particular company or this particular organization, right? So how do you do this? You have 1 billion document, and you have to go through each and every document. It's very much laborious, isn't it? So we had to come up with a system or an automated system for doing this. So that is why we depend upon these kind of NLP or natural language processing system. So what do? They pass through these different several documents, and then using POS tagging technique, we are able to identify these different the person's name or the organization's name, right? So this is exactly your part of speech tagging or that kind of techniques in NLP library, and mostly we use NLTK and spacy for this kind of POS tagging. Fine. Now we'll look into the next set of advanced pre-processing techniques. We have this NER, where I already told you, name entity recognition, and then parsing, and then co-reference resolution. Right. So parsing, we've already seen this in the first introduction to language and the context-free grammar and all of these first approach which we saw before even getting into NLP pipeline. We saw different approaches, right? So in the first approach, we looked into this context-free grammar and heuristics and all of that, and that is exactly where in context-free grammar is where we saw about parsing. So we looked into parsing of source code or the programming languages to make compilers understand the language. And here we are seeing how the parsing in the documents, parsing of documents to get each and every word, each and every string in the word is actually done. So this is kind of pre-processing. So we do parsing and then we get the NER. So we use NER based, POS based tagging for getting the NER, right? So, and then what is co-reference resolution? For example, if there is a sentence like this: Chaplin wrote, directed, and composed the music for most of his films. Here, the his, the pronouns actually represent the person, right? So we make sure that these pronouns are understood by the NLP systems, that they're pointing out to the actual noun or the name of that person. So this is called as the co-reference resolution. It makes sure there is a link between the different entities, that are the same entity which is represented differently, right? So that is co-reference resolution. And then parsing is very much straightforward. We take the POS tags or the part of speech tags and then make out a tree so that the NLP system, rules based or a machine learning based NLP systems, understand the structure of the sentence, and then using that we'll be able to recognize only those names alone for name entity recognition kind of tasks, right? So this is the whole visualization for it. So what did we do initially? So this is like, what is it? It's like a visualization of whatever you have seen till now. So we take in the whole text, we then tokenize it, and then we perform lemmatization. Before lemmatization, we perform even stemming and then lemmatization, and then we perform POS tagging. We get the different words tagged with what do they represent, what are they representing in terms of the grammar. Fine, they will say actually exactly which word is representing what tag, what part of speech is it pointing to, and all of that. And then from that we get the parse tree, the whole parse tree with all the different structures. And then from there we'll be able to get the resolution, a co-reference resolution. So with this structure, we'll make sure that the word, this particular entity, is being correctly pointed out even by its own pronoun based entity. So we make sure that these two are related or meaningfully related and understood by the NLP system. So that is co-reference resolution. Fine. So yes. So with that, we wrap up the whole pre-processing techniques. We'll even see the implementation, but you will just see the whole process now. So what did we have? We have the text first. We used sentence tokenization to spread, like take out each and every different sentence, and we got the list of sentences. And we used different processes like lowercasing, removal of punctuation, stemming, lemmatization, all of these different techniques for even processing the different sentences and getting the words properly. These are the basic pre-processing techniques. And then we perform the advanced pre-processing techniques. Advanced pre-processing techniques could be your POS tagging, part of speech tagging, parsing, co-reference resolution, all of these. Fine. So other than this, we have a lot more of the pre-processing techniques as well. But then these are the most profoundly used pre-processing techniques for most of the machine learning and heuristic based NLP systems. Fine. So that is it. Now we'll move on to the implementation part. Get hands on. So get ready with your Google Colab. And I've attached even the notebooks also in the description. So get prepared. Fine. We'll perform each of these different techniques in code now. So first, what do? We have text normalization. So here we have this original corpus. We take this corpus, we lowercase it. So or it has a collection of uppercase, exclamation marks, and different things, right? So we first lowercase this and then remove the digits using regex library. Here you can see it takes out the digits alone, and then this is given as input for another function. Here we used a string library to remove the punctuations alone. Fine. So we remove the punctuations alone here. And then we go on and remove the trailing white spaces. Sometimes all of these texts could have these kind of extra spaces before the double quotes, right? So all of these extra spaces should be removed. Even here you can see, after removing these two exclamation marks, these spaces which are here will actually remain. So that is why we have to use this. So removing trailing white spaces, and then we'll move on with tokenization. So how do we proceed or implement tokenization here? We are using NLTK library. So we'll be performing tokenization using NLTK here. So first you can see we are downloading the stop words from the NLTK package, and then we download something called as Punk, or actually it's a tokenizer. Fine, the sentence tokenizer, we use it tokenizing the sentence itself, and then getting the sentences from the whole corpus or the whole one string based corpus. Fine. So we do this, we download this Punk, and then we even import this word tokenize function, and then we can directly use it here. You can see, first of all, we just storing all of the stop words and then tokenizing the corpus from the using the word tokenize package function from the NTK package, and then we can directly see the tokenized corpus here. It's printing out all of that, and then we use a conditional statement like if conditional statement along with the for loop to parse through to go through each and every element in this list, that or list of words that is tokenized, and then we perform this conditional statement to identify whether this particular element is present in the stop word list or not. So if it is not present in the stop word list, which means it's a normal word, then it can be included in this list. So we'll get all of the tokenized text without the stop words properly. So this is the whole tokenization and stop word removal process using NLTK. Now we'll move on to stemming using NLTK. So here we directly use a constructor called PortioStemma. So there's actually a constructor or a class. Fine. From here we'll call the stem function. Here you can see stem function, and then we include the parameter word. So what is this word? This word is the element in each of this each element present in this list. Fine. So then you can see we can do the whole stemming process here. This is how it is done. So stemming process just removes a suffix, right? So that is all it does. For getting the root word or the proper meaningful unit of that word, we need to use lemmatization. So that is why we use lemmatizer here. So we import the WordNet based WordNet we've already seen as a knowledge base. So WordNet based lemmatizer class is imported here, and then using that class we call this function lemmatize function, and then we given the word which is tokenized, which is there in the tokenized corpus as an input, and we get the lemmatized form of that each and every word. Fine. So this is the whole process of lemmatization. And then now we have seen all of this implementation using NLTK, right? So now we'll see some implementation using spacy also. Spacy is a state of the art NLT uh, NLP library. So it is very much used in the industry as well. Fine. So we need to know this. So we will be implementing this as well. Fine. So now I have to download this spacy model in your local environment. So how do you do this? Exclamation Python -m spacy download encode web sm. So it is actually a model. Fine. So we were downloading this spacy and this model. Yeah. Fine. So now we'll import the spacy's stop words, and then importing spacy itself, and then loading this particular model, whatever you downloaded, we are loading this into the spacy model. We'll be using this. We'll see where we are using this. Fine. So first of all, we do the same process similar to NLTK. We store in the tokens, we store in the stop words, and then we use a conditional statement using if, and we pass through this the list of tokens using the for loop, and then we list out or filter the words or filter the tokens which are not stop words. So that is how you get this. Fine. And now to plot out the difference in performance between NLTK and spacy, we are just printing out the different set of words or extra words that are there in the result of NLTK and that are there in the result of spacy. Fine. So this is just to see the difference between NLTK and spacy's performance when it comes to stop word removal and tokenization. Fine. So now we'll move on to POS tagging, part of speech tagging using both spacy as well as NLTK. So what do? We use a spacy model, whichever we downloaded here. This we loaded here using this. We use the same model to get in the whole corpus as the input, and then we get the whole list of words or list of tokens along with their tags. How so? You can see here. So we get that. So when we pass through this whole doc based list, you'll be able to see that each and every element will have even its POS tag also. So how do you retrieve the tag? You can just write token dot or that element dot POS underscore. That is all. Fine. So it's very much straightforward using spacy. So we downloaded a model and then use that model. Here also in NLTK also we use a model, but then it's a different model. It's averaged perceptron tagger. So we use this model directly, and then we can use the POS tag function. If we have downloaded this model, then you can directly use this function, POS tag function. Before POS tagging, you have to tokenize the whole corpus. So we tokenize it, and then we use this POS tag, and then we'll get the whole POS tagging. What is this p print? I've already told you. Prettify print. So whenever it's printing out these kind of tags for each and every string, it'll be good for us to easily visualize it. It'll be much better if we print it using this kind of statement, because it will be easier for us to look into it. It'll be formatted. While printing, normal print will just print all of the statements like that. But then if you p print, prettify printed, then it'll be formatted and then printed to you, so it'll be easier for you to visually understand. So till now we have seen all of the different code snippets here. All of these were all, different pre-processing techniques using both spacy and nltk. Now we'll run all of these code snippets in Google Colab. Fine. So run it along with me. Implement all of these. Fine. So now we'll look into the Google Colab implementation of the whole code snippets that we saw for tokenization, stemming, lemmatization, stopword removal, POS tagging, all of that. Fine. So first, load the whole spacy library and then download the model. Fine. And then install this and then run this. So this is how you install it. So run these two code snippets first, and then after connecting with the kernel only, you'll be running all of this. After running, again go here, disconnect and delete runtime. It'll show you something like this. Click yes, and then again reconnect, because you're restarting the kernel or the terminal so that all of the dependencies are loaded properly. Fine. Then after it's connected, it'll show you connected, and then now go on with running all of the other code snippets. So we'll run this. I've already run it, so I'll not be running it again, but then I'll just show you how it works. Fine. So you run this, then you lowercase all of the uh, corpus, so you get this. You can see here, right? The capital letter N is now small letter, and then we remove all of the digits. So you can see here it was 4 times here, but then the number is now gone. Then you remove the punctuation, so you can clearly see here there are no exclamation marks or the stop, a full stop here. All of it is removed. Fine. And then you have removing of the trailing white spaces. So all of the white trailing spaces are removed now. See here, you can see this trailing white space is now removed. Are you able to see this? So yeah, and then we now do the tokenization now. So how do we do this? We do this using NLTK library now. So now we'll be able to run this. If you run this, it'll be loading all of this, and then you have to add this tab here. We saw the code to be only punct, right? But then it should be punct tab. Only then this will be properly downloaded, and then you run this. So you can see here. First, it got tokenized. All of these different words were tokenized. Fine, and then we removed the stop words, like to the which will be, all of these actually are stop words, and all of these are removed. Fine. Now we'll run this. We'll use spacy now. So we run this, and then from run this as well. I can see here again, tokenized corpus is again all different individual words in the sentence. Fine. All of these are individual words. And then you have tokenized corpus again without the stop words. So all of the stop words are removed here. Fine. Now the difference between NLTK and spacy would be this. Fine. Okay. Now we'll do stemming using the porter stemmer from NLTK. Fine. So we again see this here. All of the suffix around is removed. From the word finalize, we remove the suffix IZE. And yes, you can see all of the suffixes are actually removed properly. So this is the whole sentence after stemming. Fine. Now we'll run this lemmatization. Here you can see clearly the sentence's meaningful unit alone is kept. So the meaningful parts of the words or forms of the words alone are kept. But then it can even make mistakes like this. See, sometimes it can make mistakes like that sometimes. So yeah. And then we have POS tagging using spacy. So see here, POS tag, we just ran this, and then here, average perceptron tagger in English. Make sure that you add this. Fine. And then anyway, I'll be sharing this Google Colab notebook, so you can just run all of these. Fine. So tagging using spacy. You can see all of these words are properly tagged with their parts of the sentence, a part of speech in terms of grammar. And then using NLTK library, see how varied it is in terms of like presenting it. But then see the tagging words given by NLTK and spacy. See here it is in noun form. There it is properly in verb. Now we can understand why spacy is an industrial model and NLTK is not an industrial model, right? So yeah. So we did the whole POS tagging. So that is it. So we have done the whole implementation of the whole tokenization, stemming, lemmatization, stop word removal process in Google Colab, right? Right. So now with the implementation of pre-processing steps done, we'll now move on to feature engineering. So in this feature engineering, we'll be looking into two different parts. One is the feature engineering pipeline for normal classical NLP approach. Fine. That uses the manual rules and all. Fine. And then we have the deep learning approach. So in the classical NLP approach, we'll be using machine learning methods. And for feature engineering in machine learning methods, we use a lot of handcrafted rules or handcrafted processes or steps. Fine. To main goal of feature engineering is to definitely convert all of the textual data into numerical form. That is the overall goal. But then both of these two different approaches, one is using the machine learning approach or the classical approach for NLP, and then we have the deep learning approach. Both of them do this in a different way. In the classical approach, we have handcrafted techniques to convert all of these textual data into numerical form. And then in the deep learning method, we don't use any handcrafted tool. Instead, we directly take in the text and then use it, convert it into a numerical form using some libraries like the Glove or Word2Vec kind of libraries, right? So we'll look into it. See, first we'll look into the whole classical NLP pipeline overall, and then see where the feature engineering comes into play. So this is the whole classical NLP based tasks pipeline for NLP. So documents are taken in, we do tokenization and then POS tagging and then stop word removal. Before even tokenization, we do the stemming, stop word removal, and lemmatization, and then tokenization, POS tagging, and then we go on with feature extraction and then modeling. So in feature extraction, usually what happens is we convert all of these words into proper text using some technique, or we even take out only those words or those numerical representations of the words which are really needed for the task, right? So that could be a feature extraction. And then those extracted features, whichever we felt as important, those features alone are taken in as input for the models, and the models are trained on top of it iteratively. And then we have the model ready for inference or prediction. So this could be your whole classical NLP pipeline, and the feature engineering exactly comes right after pre-processing. Right, here is where it comes, and usually it is a handcrafted method that we use for specifically the task. Right, that is how we do it for classical NLP approach. And now, if you see the same feature engineering for deep learning pipeline, then you can see this. So the documents are taken in, they are pre-processed, and they're directly embedded, or they're directly inputted into a dense network or dense node
for getting the embeddings. So we get the numerical representation of the text using these structures, and this could be via your word to vec or doc to vec or glove kind of packages. So all of these packages are deep learning based packages. They are basically some dense neural network, feed forward neural network that actually numericalize the textual data, and then it will directly be processed, and it'll go through all of the hidden layers and then the output units and then the output. Fine. So this is the main difference. So what are the advantages with deep learning? Why did even go for this? The main reason is, for here we are handcrafting the techniques for uh, getting the or extracting the features, right? So it could be done for smaller data set, or it could be done for a intermediate level data set for machine learning tasks. But then if the data set is very big, then there'll be a lot of complex rules, and there'll be a lot of words, a lot of vocabulary. It will be very much difficult for handcrafting such techniques from scratch again and again for different tasks. That is where we had to come up with an approach which is more resilient to different tasks. It could be used as a standard, simple, scalable procedure that could be used for several tasks. We wanted that kind of an architecture, or that kind of a module, and that is why we went for these kind of word to vec, doc to vec, glove kind of libraries for getting the proper numerical embeddings of the textual data and then using them directly for the neural network, right? So this is the whole feature engineering in the whole deep learning pipeline. So that is it. And one problem with this approach is that it reduces the interpretability. Whereas in the classical NLP approach, we had the control of handcrafting our own functions or techniques for extracting the features. So we had the control. But then here in deep learning, we don't have the control properly, or we don't have this verifiability kind of option, because all of the word embeddings or the numericalization of the words or text is done by a neural network, where we just see the updation of the weights, but we don't see how exactly has a particular neural network or this dense embedding has come up with these set of numbers for representing this particular text. That was the main criteria. That was the main trouble. That is why it reduced interpretability. But then overall, the functionality or the performance of the model was very much improved using this deep learning based pipeline. That is obviously we have seen that already. But then feature engineering happens like this here, and feature engineering happens a different way in classical NLP. That is the only difference. And the whole major task is to just get the numeric vector or numeral vector that could be understood by the ML system for a particular text data. That is the whole overall goal. Fine, fine. Now we'll move on to modeling. Fine. So with modeling, usually we start off with simple heuristics, meaning simple shortcut strategies for making the model understand a particular task. For I have already told you a similar one for sentiment analysis, right? Where we just counted the number of positive words for classifying a particular document, or for classifying a particular review of a company. We just counted the number of positive words, and then we counted the number of negative words, and then this could be a heuristic directly. And then if the positive word is greater than number of positive words is greater than the number of negative words, then we classify the document as to be negative or positive, right? So this could be your simple modeling using this like simple heuristics. So for all of these simple heuristic techniques, we just start off with irregular expressions, and then blacklist and purchase based rules. What are these? What are these? We'll see that. Purchase based rules are simple heuristics that use customer buying behavior, like recommending popular or similar category products. So what we do, we just see manually, we just see the data set. We'll see what kind of categories is a customer buying after buying one kind of category of products, and then we just manually write down the rules. We'll write down a if condition. If a person buys this, then recommend this as well. So this could be a simple heuristic, a simple rules based um, uh, recommendation, right? So that is the purchase based rules, or it is an example of how heuristics is used, right? And then we have something called blacklist. So in you would have seen this already in spam email classification. For classifying a particular email as spam or not spam, even in Google Gmail or any Yahoo Mail or anything, in any of your email or electronic mailing applications, you could see this. So whichever email is spam, it automatically uses its separate tag and then classifies all of those emails which are spam around inside the tag. How does it do this? It does this using this something called as blacklist. So it has a list of blacklist words. So it is predefined list with some spammy domains or keywords alone that is manually typed. So it's again a rules based system. We do that and then we filter out the unwanted content around like the spam emails. So this is just an example. So usually we start off for any particular NLP task, we first try to solve it using heuristics because it's very much simple and very much straightforward, and then it's very much computationally easier. That is why. So we start off with that heuristics, we come up with the rules, and then to improve the performance or build on top of it, we go for building our model. This is exactly where we build our model. So we create a feature from the heuristic for our model or your model. If you're building your own model, it will be your model. But I'm just saying. Fine. So one problem what we found out is while we can add these kind of heuristics or rules layer by layer for very small tasks, but for complex tasks the number of rules will be adding on top of each other. There'll be a lot of rules, it will become more complex, and that is why we had to come up with a technique. That is why we had to go for modeling. Right, we came up with an approach like this for modeling and all. Fine. So this was one of the reasons why we went for modeling, and modeling helps in these kind of complex tasks where just the simple heuristics or rules will not work out. Fine. And it is also easier to maintain these kind of models because it's easier to maintain the whole system. The model learns on its own about a particular spam or a non-spam email, and then it does the task very easily. Right. So this is an advantage that the model has. The one more highlight is actually you can use this heuristic feature as an input for your ML model itself. I'll give an example for this. Take the task of spam email detection. Fine. So spam email detection, in that you have to detect whether particular email sent to you is a spam or not. So it's a classification problem. So for classification problem, we'll go with the basic classification model that could be a logistic regression. Fine. So for your logistic regression, could your input be? You could actually have your input for the logistic regression to be a blacklist word count. Blacklist word count in the particular email, that could be directly your heuristic based feature, which could be input to the ML model, right? So in this kind of things, like in this kind of scenarios, you can use heuristic based. So I told you for the classical NLP, right? We used handcrafted feature engineering techniques. This is an example of handcrafted feature engineering. And then on top of it, we use this handcrafted feature, that is the blacklist word count or the bounce rate, as an input for the model, and then we build this we train this whole logistic regression model based on that particular data set. Fine. So this could be a direct straightforward example, the simplest example possible for your for this particular case, for building a model using the heuristic as a feature. Fine, that is one possible way. And then we have something called as pre-processing your input to the ML model. So we'll take this particular example itself, like the same spam detection itself. So there, if a particular heuristic based rule or the heuristic that you have handcrafted, that function that you've handcrafted, it could be a blacklist word count or it could be your bounce rate. So with using these itself, we can actually identify, okay, if the number of blacklist word count is greater than 10, then it is definitely a spam. So if you come up with that kind of a strategy after looking into your data set, if that is your handcrafted function, then and if it properly detects or classifies the spam emails properly 99% of the times, then you can directly go and use that instead of going for models, right? You can use these kind of basic NLP based ML models directly from as an API itself from Google or Amazon or AWS. fine, and many other service providers can directly use these basic NLP tools as API, application program interface. Fine. So all of this depends upon heuristics itself. It doesn't go for any statistical, evolved statistical oriented models like the machine learning models. Instead, they go for less computationally less costing heuristic based models. So that could be one of your ways. So there are a lot of different approaches. But then when your heuristic works better than, or if it works to the best, like say 99% in this case, then you could definitely go for that particular heuristic based spam detection kind of a task. Fine. So it all depends upon the data set that you have in hand, the performance of the uh, heuristics that you have in hand, and then the whole system where this particular approach is being implemented. Fine. If the requirements are already satisfied using the heuristics, you don't need to have this model. So it could be one of the other ways also. Can even prevent. But for example, sometimes you might have an exception case for even using heuristics. So whenever there's an exception for the heuristic model, only that time you can actually use the ML models. Other scenarios, you can actually use the heuristic itself. So it'll make the whole computational process very much simple and less costly. Fine. So this could be one of your approaches. So this is how you build your model. But then if you want to make a production ready best model for any complicated or a complex task, then you have to build the model, right? That is exactly where we'll be seeing how this particular modeling happens in the production environment. In the whole production environment, we don't just rely on one ML model or one particular model. We rely upon multiple models because the data set, what we are having, what is being generated on the real time is very much complex. For a very complex data set, simple models will not work out. But then you can actually ensemble or use a lot of different simple models and then collect them together and then use them for getting the perfect model or the collective model for your NLP task or NLP system. Fine. So how do you do this? How do you collect or use multiple models? We have actually we have three different techniques. Some say there'll be four, but we'll be looking into now into only like the ensemble and stacking. That's even called bucketing and then boosting, bucketing, stacking, and then ensemble. So all of these are actually different ensemble techniques that we have in the production environment. Fine. So what are these? We'll look into this. So boosting or the ensemble is very much boosting or stacking is very much sequential in approach, meaning the output of one model would be taken in as input for the next model, and the next model will be working on top of this model's output. So it'll be sequential in nature. That will be stacking or boosting. So these two approaches rely upon this kind of a scenario. Like there will be multiple ML models. All of these would be sequentially connected so that wherever this particular first model makes a mistake or error, those error filled predictions would be rectified by the second model, and then the third model will improve that further, and then fourth model will improve that further. It will be sequential. The performance also will increase properly with the sequentiality. Fine. So that could be what your boosting or your stacking method. Okay, that is one thing. And we have one more method called as model ensembling. So in ensembling, what we do is we apply the same principles of democracy. We take in all of the models, we get all of these models different predictions, and then we use something called as voting mechanism so that each model will give us some particular vote. If it is a binary classification, if this particular whole system is for binary classification task, then each model will be giving me either one or zero. So one or zero, 1 0 1 0 1 0. We'll take an average of all of these numbers. Like we'll sum up all of these predictions, and then we'll get an average of the prediction between 1 and 0, and then we'll get the a whole process. Like we'll get to know, we'll do a weighted average. So there are different techniques for getting this vote count if it is a binary classification. So we do that kind of stuff, and then we say whether this particular prediction for the whole NLP system could be 1 or 0. Is it this class or that class, or class A or class B, right? So this is the ensembling technique, which uses voting mechanism and all, and then takes all of the prediction, all of the models be processing the information parallelly. Fine. They'll be parallelly processing the same information or different parts of the information. And then they'll give us a proper output. Fine. So this is ensembling. And stacking is totally different, where we don't use parallel procedure, we use sequential procedure, and that is what is called as stacking or boosting. Fine. So now I hope you understand this. So you can directly see here, this is ensembling. We have different models. We take prediction from that, and then we get to the next level, that will be meta model. That will take, which this model actually will take all of the predictions of this ensembled or multiple models that have done the processing parallelly, and then we get the whole final prediction. There's the whole thing. Fine. So here, this is actually an like a combination. It's a hybrid of ensembling and stacking, because we are doing an ensemble here. If it was a truly ensemble model, then we'll just get the voting mechanism here and then directly get the prediction. But then all of these models output is getting into another model as an input, then it becomes a stacking kind of a problem. So usually in the production environment, we either go for stacking or boost ensembling, or we come up with a hybrid approach. Fine. It depends upon the task at hand and the performance of the models that we have and the reliability of these models for complex data set. Fine. So real-time data set is very much complex. It is not a Kaggle data set. Kaggle data sets are very much simple, but then real-time data sets are very much complex in nature. They might have a lot of issues. Some of the values in the columns will not be even filled. It'd be empty. So all of those different things, different challenges are there. So you have to rectify each of these challenges, use some imputation of data, and then there'll be some class imbalance kind of problem. So all of these are different problems. We'll look into that later. But then now I'm just going through the whole NLP pipeline as an overview. This is the second lecture, right? Very much simple. So in a whole pipeline, we're just seeing the modeling. In modeling, we saw we saw that we have to start with heuristics, and then we saw how can we build our model using heuristics itself, and then we are seeing now how can we come up with a production ready model, right? So yes. So what are the other practices? Ensembling and stacking is one of the methods. What is the next way to make it production ready? Better feature engineering. So for both API based and custom built models, feature engineering is an important step and it evolves throughout the process. Yes. So with respect to the performance of the model that you have trained, will decide whether a particular feature is good for the training or not. Fine. We even use some different methods, statistical methods, to identify whether a particular feature is good feature or not. It's called as, we use something called as heat map. We identify, it's actually correlation between the independent variable or the inputs and the target variable. We'll identify the correlation between these and then say whether a particular feature is good for this particular prediction or not. Fine. So these kind of different techniques are there for feature engineering itself. We'll look into this in detail in the further lecture, but it's just the second lecture. But then, so yeah, better feature engineering will definitely lead to better performance. And for instance, there are a lot of features, then we need to even feature select. So I told you, if there are a lot of features, we need to select the features using these kind of different statistical techniques. Correlation could be one of those. Fine. So there is better feature engineering. And then we have transfer learning. In production environment, we have to make sure that we don't reinvent the wheel. We make use of the wheel and then build on top of it. That is what the production environment is mainly about. Fine. We don't reinvent the wheel. So that is why we transfer the learnings of the pre-trained models. So already there are a lot of pre-trained models, right? Pre-trained meaning already they're trained with larger corpus of data by a big tech companies like Google or Meta or your AWS, Amazon or Apple. So all of these different big companies, they open source many of their models. So they train their own custom model with their own data sets. That data set could be very huge. They train on it iteratively and then come up with the best parameters. So they and get the best performance for this model for the whole corpus of data. And then what can we do is we actually open source this, so all of the parameters are actually properly optimal for predicting or coming up with the best result, right? So when they open source this is all available. All of these parameters are available to us. So instead of, let's say, for example, you're building the particular a model for a particular task, instead of randomly assigning some initial parameters, we can actually use this pre-trained models parameters and then build on top of it. That is why I told you it's not reinventing the whole thing. We will not just train our own model with random initialization again from scratch. We don't need to do it from scratch. You don't need to train the whole model from scratch with larger data. Instead, we can use an open source model which is already having the optimal parameters and build on top of it. We fine tune it. Fine. So this is what transfer learning is. So it is almost like a teacher to the student. So what does a teacher do? Like actually the student has the ability to learn everything on his own, on our own. Fine. They can actually just go on, observe nature and then come up with their own physics also. But then why are the teachers even teaching you all this? Because they are giving you the initial parameters. You understand the initial parameters that we have already trained on, and then you can actually build on top of this. You can build knowledge on top of this. Fine. So that is the whole transfer learning technique. So yeah, already told you about this BERT. BERT is the Google's open sourced large pre-trained transformer model. So yes, instead of training from scratch, we do this, improving downstream results. So it also improves the downstream results because we're not training it from scratch. We start off from an optimal parameter. So the number of training iterations required will be a little less, but the performance will be very good. So that is what we want for the production, right? We want something that works in the production or the real time data. So that is why we rely on this. Fine. Now, sometimes what we do is the prediction of the model will not be just that perfect. The prediction of the model or the whole pipeline would not be that perfect. So that we apply some kind of heuristics on top of it. I'll tell you an example itself. So you have this ChatGPT, right? So initially, in the initial months of release, what happened is ChatGPT started releasing, started printing out contents that are very much um, invading privacy sometimes, or it could be even something wrong, right? It could be even controversial. So all of these controversial questions were asked to ChatGPT, and it started even generating controversial answers. So the company was already small, and then they didn't want to get into this controversial kind of things. So that is why what they did, they added some kind of top players. So they added some rules and regulations on top of their model's prediction, so that whenever a particular answer is having some kind of blacklisted word, it could be a rules heuristics. Again, they use heuristics. Even OpenAI, for filtering out the responses of their model, they use the heuristic rules. So they came up with the rules and rules based function to filter out the response of the model and then get only the best or the diplomatic answer to the user. Fine. So this is just an example of how reapplying heuristics on top of a model's prediction works, even in real life, even with even the large language models. Fine. So this is it. So ML models aren't perfect, even deep learning models aren't perfect, even the large language models aren't perfect. So we apply heuristics or domain knowledge at the end to correct the common errors. It need not be even domain knowledge, like it could be a common sense, like in this kind of scenario for the large language model, specifically when you're talking about a controversial political topic. Fine. So yes, this is the whole process. So yes, so now we'll just see the different decision paths that different data volumes require, right? So for the whole modeling process, we have different decisions we can actually take with respect to the data volume. Fine. And even with respect to the data's quality, we'll be able to decide a particular model or a particular pipeline only with respect to the data, only after we know about the data's quality, the data size, and all of that. Fine. So what do you do when you have a large volume of data? You use techniques that require more data, that is your deep learning methods, right? So you can use richer set of features as well. And then if the data is sufficiently large but unlabeled, we can also use unsupervised techniques, unsupervised learning techniques. So this is the path you can choose when you have large volume of data. And examples of that could be if you have a lot of reviews and metadata associated with them, we can build a sentiment analysis tool from scratch using deep learning. And even you can use the rich set of features as well. And if it is unlabeled, you can use even the unsupervised techniques. Very much straightforward, right? If the data volume is large. Now we'll see if you have data volume is small, then you must, you must start with ML techniques. Before even ML, you have to go with heuristics and then go for traditional ML solutions that are less data hungry. You can also adapt cloud APIs and generate more data with weak supervision. I told you about Snorkel, right? Snorkel is one of those models with which you can use weak supervision based data labeling, and you can generate more data using NLP org, data augmentation technique. And then you can use transfer learning if there is a similar task that has a large data. Fine. So it means there's a similar task where a model has been trained on a large data. That is when you can use transfer learning. So you have a small data volume, but then you can use transfer learning based models that are open sourcely available. You can use them directly because they're already trained on large data set, and then you can just fine tune them with your small data volume. Fine, that could be your one of your ways. But then you have to start with heuristics and rules, and then proceed further with less data hungry ML models. And then if you have to improve the performance even further, then you can go for transfer learning techniques. Fine. Or you could increase the number of data points using NLP or data augmentation techniques. And then if you want a supervised kind of procedure for your pipeline, then you can use auto labeling methods using Snorkel or other tools that we have discussed before. And then use a transfer learning technique. Fine. It's very much straightforward again. Examples could be these are, yeah. So for every single project, whenever you're starting a new project, you usually have very small data about it because you'll have lesser number of information, right? The number of information sources that you would have been very less. So that is why you would have a smaller data set whenever you start a new project. So, but with time, you'll be able to increase the data set. You'll be able to find more sources, or maybe you can tell your client about your requirement. Fine. So tell your client about the data requirement. You'll be trying to solve their business requirement, but then you will try to say that okay, for this particular business requirement that you demand, I will need this much amount of data to actually give you the best performance. So that is how you get communicate the technical requirements for developing your own NLP system for the client. Fine. So this is how it happens. So this is an example. Now we'll go for data quality. Where the data quality is poor and the data is heterogeneous in nature, more data cleaning and pre-processing might be required. There is no other way. If the data quality is poor, you have no other choice. You have to do data cleaning, and then pre-processing is a compulsory step. Only then you can actually proceed further, because data quality is utmost important. Even if you have small data, or even if you have a large data volume, okay, if you have a large data volume but then the quality of data is very poor, then you must apply data cleaning process and even the pre-processing techniques. But even when you have a large data set, it's essential. Fine, because data quality is profoundly impacts the performance of the model. So it is very much important. And then we have the example for this particular case. So this entails issues like code mixing, different languages being mixed in the same sentence, unconventional language, transliteration, or noise. So we have already seen this kind of an example before, right? With a Singlish for a sentence that was told or seen in a social media channel in Singapore. So people use different languages in the same sentence itself. So it could be even translated to English, but then they're not really English. They would have been in Cantonese or Mandarin or Tamil or something. some of the any Southeast Asian languages. Fine, these are actually real issues. So what do we do in that case? The data quality is already poor. We have to do pre-processing. You must clean the data. That is the only process. Fine. So, and when even the noise is there. So noise is usually there whenever you web scraping data from social media, because people write all kinds of stuff, a mixture of emojis, mixture of different languages and all of that. You will find all combinations of data there. So you will have to clean the data and then pre-process it, only then you will be able to go on with the other stages of the NLP pipeline. Okay. Now we'll go for this process. When data quality is good, then you can directly apply off-the-shelf algorithms or cloud APIs more easily. If the data quality is good, it's actually a boon to you, or it's a boon to an engineer. You can directly use the algorithms directly, and the cloud APIs could also be used directly from Google or AWS. This could be the example for a source where the data quality is good, could be your legal text or newspapers. Usually the data, whatever you get from the textual data, what you get from there is very good. Fine. And then you have data consists of full length documents. For this, the length of the data is going to be very huge, and even the sentences are going to be long. So choose the right strategy for breaking the document into lower levels, like paragraphs, sentences, or phrases, depending upon the problem. So in this case, when the this is not, see, there is a major difference here. Full length document is different from this large data volume. Large data volume means the number of data points is more, but here we're talking about full length documents. The number of data points might be less, but then the data point itself is longer. So how do you process them? There's no other way. You have to break it down into smaller levels, like tokens, and first sentences are first even paragraphs, and then 10 sentences, and then phrases, and then words, tokens. As per the problem, you can do that, and then proceed further with your task at hand and the model at hand. Fine. So example could be a document classification and review analysis. For both of these tasks, your sentences could be very long. It could be even a paragraph. Fine. So in that case, you have to break it down, do a lot of pre-processing. Fine. So these are the different scenarios we saw. So for each and every different scenario, we had this different solution, right? So this is the whole decision path that you have to take up when you have a particular data attribute like this. Fine. I hope you understood. Yes. Okay. Now we'll move on with the next stage of the NLP pipeline, that is the evaluation. So don't even read this, it'll be very much huge, but then I'll tell you directly. There are two types of evaluation. One is intrinsic, other one is extrinsic. Intrinsic evaluation's main aim is to evaluate the model performance for a particular task directly. You will directly evaluate how well a particular model is performing for this particular task alone. For example, if the task of the model is to just classify, then my intrinsic evaluation would be just seeing how much accuracy is the classification having. What is the performance of the model when it comes to accuracy or precision or recall? Fine. This could be, all of these could be your intrinsic evaluation. But then if we want to know the extrinsic evaluation is done by the external people or people like the client. Client actually does the extrinsic evaluation. So he comes up with the numbers or uh, key performance indicators, KPIs, to say whether the model is impactful for their solution or not. Is it creating some difference for their solution? Is it really giving the solution that they want or not? Fine. For them, the end result or end business result or the economic result is what matters. So their evaluation will be mostly based on their business domain or their problem statement or their requirement domain. Fine. But then intrinsic is very much technical. Technical evaluation is more intrinsic, business oriented or solution centric evaluation could be more extrinsic, because the stakeholder is the person who would evaluate my solution, the solution that I come up with as a technical developer. Fine. So that is the main two differences. It's very much straightforward. So there are a lot of different metrics in when it comes to technical evaluation or the intrinsic evaluation. We'll see all of the different technical uh, intrinsic evaluations in NLP. There are even a lot more, fine, but these are the most fundamental ones that you must know, fine. First, it starts with accuracy, then precision, then recall, in F1 score, AUC, area under curve, MRR, mean reciprocal rank, and then root mean square error, and then mean absolute percentage error, and then blue is bilingual evaluation under study, and then meteor is another full form is there, and rouge, and then perplexity. Most of these blue, meteor, rouge, and perplexity, all of these are used for large language models, are text generating large pre-trained transformer based models. Fine. For all of those kind of models, we can actually use these metrics. Other metrics like the this mean absolute percentage error, root mean square error, mean reverse ranking, reciprocal ranking, not reverse, reciprocal ranking, and then area under curve, F1 score, recall, precision, accuracy. All of these could be used for your different basic NLP tasks or intermediate level NLP tasks and all of them. Fine. So we'll see each one of them with distinction properly along with a formula. Fine. So accuracy just tells you the proportion of total correct predictions. So out of all the predictions, how many of them are correct? Truly, which was correctly predicted as truly positive or truly negative. What are these TP, TN also represent? It means the whatever prediction the model made, that is coinciding with the real data. That is when you tell it is truly positive and even truly negative. So if the real data is negative and the model predicts negative, which means it is truly negative. And if the real data is positive and the model's prediction is positive, then it means truly positive. And false positive means the model predicted something and it's not coinciding with the data, but the actual data is negative, then it means false positive. And if the model is predicting it as negative, but the actual data is positive, then it means false negative. Fine. This is the whole understanding of the terms here. So the proportion of total correct predictions could be the total true positives and the true negatives over all of the different predictions. That will be giving you the accuracy. Now we'll go for precision. Proportion of predicted positives that are correct. So what are these? Proportion of predicted positives. So whatever positives that the model predicted, out of those positives, how many of them are truly positive? That is precision. So what are the true positively predicted terms? Model predicted positive here, and it is also, and the real data is also positive, which means it's truly positive. Here in this case, model predicted positive here, and the real data was negative, something else. So it is false positive. So out of these true positive plus false positive, whichever is true positive, that will be giving you the precision. It means if a model tells this particular classification to be positive, or if the classification is class A, then it is very much precise. It says, okay, we can actually say the precision of the model is very good. We can say, okay, if it says it is positive, then definitely it is positive. That is precision. And then you have recall. Recall is proportion of actual positives correctly identified. So here we get the actual positive, which means even the false negatives, the model predicted it to be negative, but the reality was positive or true. In that time, it becomes false negative. So we want all of the positive, actual positives to be predicted correctly. So we take the correctly predicted positive outcomes of the model, and then we retake the ratio of that along with the total number of actual positive outcomes or actual positive data points. That will give you recall. Precision says out of all, if it says positive, how much shall I believe it directly? There is a minor, like very minute difference between these two. Here we are talking about only those predictions whichever model predicts it as positive. So we are more model centric. In precision, we are more model centric. We say, okay, out of whatever the model predicted, how much of the prediction is actually true? Out of how much as the model predicted as positive, how much of the predictions are really positive? That is precision. Recall says, okay, we have this is the true data. We have the reality is this. Out of all the positive real data, how much of these was captured by the model? So we in the recall is more data centric. Fine. So how much of all of the positive ground truths, how much of the positive ground truths were captured by the model? That is recall. So that is the major difference. So where can you use these two? You can use before that even accuracy. Accuracy can be used to classification tasks like sentiment analysis, natural language inference, and then paraphrase detection, right? And then we have precision. Precision can be used when false positives are costly, which means the model predicts it as positive, but then the actual reality is negative, which means it's a false positive. So in the case of disease detection, if a model says a person has this disease, but then reality he doesn't have, then it'll be a big issue. That is an area that we don't want the model to have this kind of false positives, right? So that is where a precision is real. So in Medicare, like in the healthcare domain, mostly we see for if you're using classification problems or classification models, the metric that we focus on is precision. Fine. Now we have the recall. Tasks where finding all positives matters, like search, e-commerce. So we have so here it's more data centric. Tasks where finding all positive matters. So the real positives are here, ground truth is here. We want a model that is able to capture all the positives. That is recall. But if you're totally depending upon the model, if the model says something positive, and if it is how much can I believe this model that this will be definitely positive? That is precision. Fine. I hope you understood the intuition and the whole meaning between meaning of these uh, metrics. Fine. Next one is the F1 score. 2 times the precision into recall by precision plus recall. So it's a harmonic mean of precision and recall. This is just a balanced term or a metric to get a balance between precision and recall so that we can use it for tasks that require both precision and recall. That could be your classification and sequence labeling, entity extraction. That kind of tasks require a balance between both precision and recall. That is why we got up with this um, new metric F1 score, that is a harmonic mean of precision and recall. Fine. Now we'll go for area under curve. It measures model performance across thresholds. So for evaluating classification models, regardless of threshold, we use this particular metric. Fine, it's very much straightforward. And then we have mean reciprocal ranking. So for search and retrieval tasks, you need to actually rank the search result, right? You'll have a lot of links that is or a lot of information that is retrieved for a particular query. So in that you have to rank which one comes first, second, all of that. For that we use this metric. So how is it? How is the model ranking the different information? Is the ranking correct? For analyzing or checking out that, we use this metric, mean reciprocal ranking. So it takes the average reciprocal rank across queries. Fine. And then you have the root mean square error. This is very much straightforward. I think if you're coming to NLP, you would have learned machine learning. And in the machine learning, if you have learned, the fundamentals are linear regression and logistic regression. And I think for at least for the linear regression, you would have use this as a metric for evaluating your model, right? So it's very much straightforward. Root of average squared prediction error. So we have the prediction, we take the difference between the prediction and the actual value, and then square it and sum it out, and then take the divided by the number of data points that will give you the average, and then we take the root of this average or the mean. So for regression tasks, stock prediction or temperature prediction, you actually use this particular evaluation metric. And then we have MAPE or mean absolute percentage error. It is same as this, but then here we don't take a square root. Instead, we take the absolute percentage error. That is all. We take the percentage errors across predictions and take the mean of it. That is what we do. And it is mainly used in evaluating regression models with percentage-based accuracy. Fine. And we have BLUE, that is bilingual evaluation under study. N-gram precision with brevity penalty. Don't get confused with this brevity penalty. You can actually, if you want, if you're more curious, you can actually search it out in the internet. But then I'll just give you a very small description of what this BLUE does. So you have a sentence, it will be translated. So mostly it is used for, you have to understand that this particular metric is specifically used for translation or summarization or sequence models. If you have a task that requires sequence of inputs and then it requires even the output to be a sequence, then BLUE is your correct person for checking out the performance of a model. Fine. So what it does is it takes in the whole sentence. There is something called as n-gram. Gram literally means the number of tokens. Fine. So n-gram means n number of tokens. So unigram means one token, bigram means two tokens, 3 gram, 4 gram. So we have a combination of, or we connect group of words together in a sentence. We come up with the metrics or count for the group of words that are there in the sentence, and then we compare the actual source sentence or this input with the outputs, same number of words. Fine, we compare the vectors of these, and then that is how you get this. So you get the probability of different n-grams, how much are they there in the output, and then all of these different probabilities. For one unigram, you'll have a probability p1. For bigram, you'll have a probability p2, and for 3 gram, you'll have a probability p3 and then P4. You square root all of these, P1 into P2 into P3 into P4, and square root all of these, you'll get the BLUE score. Okay, this is one of the ways. And there is another formula for this using even logarithms in it. That is a more complicated, but then this is a smaller version for you to understand just what this BLUE is and how it comes up with the metric to evaluate the translation. And you can directly say that the evaluation metric is between 0 and 1 for BLUE. For others, it's very much straightforward. Most of you would know this. Others, but then for BLUE, some of you will be very much new to this. For BLUE, the range of values of evaluation could be 0 and 1. If it's closer to 1, which means the sentence is translated very good or the summarization is very good, it means that. For 0, it means there is no correlation or any translation between the input and the output. Fine. So 0 is way bad. 1 is good. Same applies for Meteor. And it is specifically for text generation tasks and it allows loose matching between using linguistic rules. Fine. And precision recall with synonym and stem matching. Fine. I'm just giving you this definition and the formulas, but then the formula for meter is very much bigger than this, and even BLUE is very much bigger than this. I'm just giving you a introduction to these different metrics. Others were all actually fundamental, but then these are mostly used for large language models, and they were introduced very recently. Fine. So these techniques, and we have perplexity. It measures how uncertain a language model is when predicting the next word. So the lower the score is, the much better it is. So it is used in evaluating language models and text generation tasks. That is perplexity. Fine. So these are the different metrics. I hope you understood at least the fundamental ones properly, at least till BLUE. Meteor, Roj, and perplexity, you will require even more understanding of how these text generation works. So we'll look into these metrics when we are discussing about large language models or the transformer based models. Fine. So yes. Now we'll move on to the extrinsic evaluation, which is very much straightforward. I've already told you this is very much task specific metrics. We'll even cover it in the next chapter, but then these are basically for coming up with a checkpoint on whether a model or a particular solution is able to give out the result that is required for the business or the client. Fine, that is the extrinsic evaluation, only given a small description. So it checks whether a model is able to achieve the business goal or not. Fine. So most of the times, these extrinsic evaluations done by the client or the stakeholders. So, and it is very costly also to get a third party feedback of our NLP system, right? So that is why most of our evaluation usually is based on intrinsic evaluation. That is, the same technical team that is developing a particular system will actually do this intrinsic evaluation, and we give more priority to the intrinsic evaluation, because most of the times when your intrinsic evaluation is the highest, then extrinsic evaluation will somewhat be good. Fine. So if your intrinsic evaluation is very good, then definitely your extrinsic evaluation has a lot of chances or a lot of probability that it will be good. That is the overall understanding in the production environment. Fine. So these are the two different evaluation metrics that we saw, like evaluation systems that we saw. Inside intrinsic evaluation system, we saw a lot of metrics. We saw the formula of them and then the definition and where they're used. Fine. So with this, we end the evaluation. Now we'll move on with deployment.
So now we'll look into deployment. So when do we usually deploy? We deploy a model whenever this model is ready for production and it is robust for handling the real world problem. Fine. And first of all, you have to remember this: whatever NLP module that we are developing, starting with all of these pre-processing, feature extraction, modeling, evaluation, all of these are a very small part of the whole business problem. That is why you require a team for doing solving a real problem. Fine. So usually when you develop an application or when you're developing a software solution for a particular problem, you need a whole team, because you have a lot of things to solve there. You have a lot of things to even address there. You have to make sure where this data is coming from. How are you capturing this data? Where is this data coming from? How are you capturing data? How is it formatted? Where is the data stored? How is the data moving? Where is it going to move? How is it going to enter the model? How is the model going to react? How is the output of the model going to be delivered to the customer? And how is the delivery of the output of the model useful to the customer, and how can we make the output of the model useful to the customer? What other layers on top of this prediction should I add so that it will become even more economically viable for the economically more productive for the client? So all of these different things need to be addressed when you're deploying or when you're developing a whole application or a solution for a client, right? So in the real world scenario, all of this NLP modules that you saw till now, this whole NLP pipeline would be just a small module. The small module will have these many different stages of development, or these many pipeline things will be there. But this will be a small module. You have the model deployed there, you will have the model deployed there, and then the model will predict. And but then you have to decide, now you have to integrate this model along with the existing applications data pipeline. So the data will be coming, the model will be useful only when it is able to get in the data, ingest the data and get the output. So how will it get the data and from where will it get the data? So you have to make sure that this model is properly integrated with the data pipeline in the application whatever is you're having. Fine. So this is where the whole deployment comes into play. So you'll have to maintain the whole process. You have to make sure that this data pipeline is properly getting fed into the model, and then the output of the model is perfectly retrieved, and this output is properly transformed again for the before displaying it in the dashboard for the customer. Fine. So this could be an analytic solution, or all of these different components of the application should be integrated with the NLP module. So this is exactly where the deployment comes into play. So many of you would have developed some ML models using Kaggle, right? The reason, even after doing so many Kaggle projects, people are not getting recruited by the recruiters is because most of them know how to develop models now because of the Kaggle data set and the competitions. But then they don't know how to deploy this model and then make it production ready. Making a model production ready is very much important in the real industry standards. Fine. So you'll have to know how to create this machine learning model or a deep learning model, how to deploy it in the cloud or an application, how to integrate the data pipeline with this model so that it's able to ingest the data, and then how to retrieve the output of this model, and then how can I do some analysis or transformation on top of this output to display to the customers, the clients. So this would be the whole deployment phase. So you have to integrate with these many different components. So this is exactly where many of the current NLP or machine learning engineers or people who rely upon only Kaggle projects or academic projects are not able to uh, get a job, is because they lack the real time industrial exposure or industrial experience of deploying a model and then integrating them with the data pipelines. So this is the most important part for improvement for many of you. So you need to concentrate in this as well. This is also very much important. And what happens usually is when a model is deployed into an application, when it's integrated in this application, we'll have to have a portal or a dashboard that is able to monitor the performance of this model. So we'll have to see continuously monitor what kind of data is getting in, what kind of output is getting out, what are the parameters of this model, how is it predicting all of this. So all of these different things should be monitored properly through a dashboard. So that is why we have a performance dashboard, right? So performance dashboard says how well is the model performing, and then the latency, how many minutes or seconds or time duration does the model take to come up with a prediction or come up with an outcome or a classification, right? All of these throughput is the number of data points it's able to ingest at a time or in a time step, throughput. And the latency of the model, and then how well is the accuracy getting destroyed with some other new data point, or how is the model reacting. These kind of analytics of this model would be monitored, and they'll be displayed for the backend developer so that he can improve or update the model whenever it is necessary, right? So this actually is the whole deployment phase. So deployment is where you integrate the model with the remaining multiple parts. It's like adding a puzzle in a whole puzzle card, right? Having like just one piece in the whole puzzle card. You have to make sure this piece fits perfectly in the whole puzzle card, right? So that only then this whole puzzle would be completed. It will be meaningful. Only when it is fitted properly will the whole puzzle be meaningful. Similarly, with the whole solution, only when the model is properly integrated with the data pipeline and the how it is transformed, how is the output retrieved, when it is all perfectly in sync with the other modules of the application, only then the whole solution will be robust, and it will create some economic value for the client, right? So this should be your understanding of how deployment takes place and what should be focused, or what should be your checkpoint or checklist when you're doing deployment. Fine. So yes, so this is the whole deployment. And we will also have to decide whether you're going to make it as a web service or you're going to do a web batch processing. What does it mean? What does it mean like you're going to make a web service or a batch process? It means, are you going to collect some amounts of data and then send that amount, like for example 10 data points together? Are you going to make it into a batch of data points and then send it as an one batch wise? You're going to send it to the model or make the model in just that way, or are you going to make it a streamlined model, like continuously the data would be coming out through the internet as a web service? It will be coming through the internet through an API or something, and the model will have to continuously ingest the input data and then continuously come up with an output. So are you going to make it work like that, or a streamlined continuous data having or data ingesting real time streamlined model? Is that going to be a deployment style, or are you going to make it batch wise predict the outcome? So these kind of different decisions you have to take with respect to the task that you have at hand. Fine. I'll tell you, for a email classification task, you could actually use a batch wise data. It need not be a continuous streamline, continuously ingesting model, because the emails will not be, it depends upon the traffic of the system also. If the email traffic is very much, like for each and every minute you're receiving more than 16 emails, then you'll have to use a streamlined model kind of pathway or a pipeline. If you're not having that that much traffic in terms of emails, the number of emails you receive in a minute, then you could go for batch wise processing. Batch processing, it's called batch processing, and then streamlined real time processing, right? Continuous processing. So these are the two different ways you can actually integrate the data pipelines into a model and then process it. So all of this is actually where the real time industrial knowledge comes into play, right? This is the whole deployment strategies now. Fine. Now we'll go for monitoring. Monitoring, I've already told you, we have a performance dashboard. We monitor each and every aspect of the model. How is the model reacting? How many data points is it ingesting per second or per minute or per hour? How much output has it given? Is the given output correct? Is the performance of the model good? Is the accuracy of the model good? Right? These kind of all different metrics of seeing the current state, the past state, the past performance, and then saying, okay, the model is doing good, will be able to make it even better. So that kind of inference, we can only get it only with monitoring the model continuously, monitoring the parameters of the model continuously. So you do this, you usually do that using the performance dashboards, right? We for tracking the key metrics and parameters. So we do this mainly to maintain the consistency of performance of the model, and all of the metrics of the model or the model performance is continuously good, right? So yes, and then you have model updating. So here is where you start getting new data points, and then the model is not performing good. So the backend developer actually tells it to the ML developer, okay, your model is not performing good. I'm able to see in the performance dashboard, the accuracy has come down suddenly because of some new data points. I think we need to update the model. And then the ML engineer comes in and then takes gets hands on with the model and then improves or updates the model. Right? This could be the whole procedure. Hope you understood. Now we'll see the project attribute and the decision part. So before we saw like with respect to data size or data's quality, we decided which pathway or which kind of procedure can we move forward for solving a particular business problem or developing a particular NLP system. Now we'll see what kind of business attributes will lead to what kind of decision paths in terms of deployment and even monitoring and model updating, all of these procedures. Fine. So basically, there are four main project attributes, and for four of them, we have the examples. I'll first go in the examples and then tell you the decision paths. Fine. So here is an example. Here is the first example. So we have abuse detection systems where users flag data. Fine. So more training data is generated post deployment. Yes, right. So in this, take this particular abuse detection systems, right? So here, that told the users flag the data, which means you'll get a lot of training. Labeled training data would be generated after deploying that whole module in the system, right? So you're deploying the model, and people are using it. People are flagging the new data also, and these new data that is generated are actually done after deployment. That's why it's called post deployment, and it is all getting labeled by the users directly. That's why it's a flag data. So in this scenario, we are getting more training data after the deployment. So what do you do in that case? So we can actually make up a path or a pipeline or an application where the model retrains on its own regularly as per schedule or something. So you can actually make it a daily schedule for a model or a daily script running for a model to retrain itself with all of the collected data for the day. Right? You could do one of that, or either you can actually do it for like each and every 1 hour. The model will actually learn from the newly labeled training data that the users have generated. Right? The other told something like extracted signals. Once deployed, extracted signals can be used to automatically improve the model. What are these extracted signals? So usually in this particular, you take even this particular example. So here what happens, users are flagging the data. So users are doing some particular action, right? These actions are actually the extracted signals. So it could be a user feedback or a user action or a flagging of that particular data. All of that is actually are external signals. So these signals are external, and they are like the feedback for the model, and they become like labeled data set. They create indirectly the labeled data set, training data set for the model, and then you can actually make it make a script or learn make the model train itself online for each and every particular time period, and then automatically it can train on it and then become better at flagging, or better in this particular case the model will become better at flagging the abuse, right? Or it can become even over the time, it will become even more better in its performance. A best example for this, other than this, would be the recommendation system that is there in your Amazon or Netflix. So there, whenever in at the start of the when you start the account in Netflix, the videos generated to you would be random, right? Like the video displayed to you would be random. But then once after you have looked into it, and then once if you have engaged with the video or the video content, or liked the video or done something like that, you would have created a lot more training data for the model that is there in Netflix, like the recommendation model. So the data that is generated by you would be used by the recommendation engine of the model on the go on a regular basis, so that every time, like right after some 2 to 3 days, you'll see all of the contents in Netflix that are very much favorite to you, or very much uh, interesting to you, right? So this is the best example of this particular scenario. The Netflix videos that you watch, or you by mistake, sometimes you become even binge addicted to it because of the algorithm that is actually training. Like the model is trained on the go with the real time data that we are generating while watching the content. All of the signals that we are giving will be taken in, will be extracted, and then it will be used, right? This is all happening even after the deployment. So this is how robust the model uh, is actually in production environment. So most of the companies use this, starting from Amazon, Instagram, Meta's, Facebook, and then YouTube. Everywhere, wherever you go, this particular thing is actually happening. Even the YouTube, whenever you like a particular video, it is training on your particular custom data, and then coming up with a better recommendation for you, right? So all of these are all of these come under this particular scenario. Okay, fine. First attribute done. Next, we'll see second attribute is training data is not generated post deployment. Okay, this is a very difficult situation. Here, training data is not generated after even the deployment. So what do you do in that case? So here, you can see the example could be a subset of a larger NLP pipeline with no direct feedback. So it's a larger, very big NLP pipeline. So you would not have this particular feedback, direct feedback for this particular small model. So what do you do in that case? There's no other way. Whatever data is getting generated, if it is not labeled, if it's not becoming a proper training data, then you will have to manually label it and then manually retrain a new model from scratch. There's no other way other than that. So each model, so if you want to improve the whole model performance after even the deployment, then you will have to again create a new model, build it manually, and then train it manually from the scratch again. But then you can actually improve on the existing model that you already deployed, but then again you will have to use the new data, train on the new data that is coming up real time, and then do all of this will have to be done manually. In the previous segment, what happened here, you have done it automatically, right? You can automatically make the model improve by scheduling a training process in a particular day, or within a particular time period, right? But then here you'll have to do it manually. There is no other way, because the data is already not good. There is no labeling of the data, so manual labeling need to be done. After that, you have to train the model. So this is one okay, this is one scenario. I hope you understood the attribute, like what scenario this is, what example this is, and then why this decision path was taken. Similarly, I hope you understood the intuition behind this decision path. Now we'll go to the next scenario. Okay, now you have a requirement like where low model latency is required, or model has to be online with near real time response. I told you right before that there can be a situation where the latency need to be very less. or the quick reaction of the or quick output of the model is needed. So here, okay, we'll see the examples here. Systems that need to respond right away, like any chatbot or an emergency tracking system. So all of these kind of NLP systems need to actually react very fast. They will have to be very much quick in their response. So what do you do in that case? What decision path could you do in that case? Need to use models that can be inferred quickly. So you need to use a model that is fast in its computation and then output retrieval. Another option is to create memoization strategies like caching or here having a substantially bigger computing power. So you have two different strategies here. Either you will have to have a greater computing power, meaning you have to make a bigger computing GPU based models where the model can compute fast at much faster rate and then give us the answer or the output quickly, or else you'll have to you have to mimic what to say. Instead of computing the whole answer, you'll cache it, meaning you will store other input datas and cache it or store it in RAM in your system so that it can be fetched on a short-term basis. Right? It's like almost like faking, but then without any real computation. But then this is also one of the strategies. When low latency is required, there is only two options. You have to either improve the model significantly, or come up with a better architecture, or come up with have a good computing power, or caching or memoization strategies like caching. Caching meaning you'll save parts of the output or parts of the previous outputs in RAM, in temporary memory of the system, of the NLP system, so that it could be retrieved fast in a quicker way for the new data, right? For the new input data point, we can give this previously computed output itself as it is stored in the cache. If it is similar to it, we can give the previously saved output itself instead of computing again for the again now and then getting the answers delayed. We can give it quickly like that. So that is one of the strategies. Fine, that is memoization technique or caching. So here they are given only two, but then we have three. Either come up with a better architecture, or have better computing power, or cache it, or use RAM. It's like a cheat code. Using RAM or cache is actually a cheat code for these kind of low latency requirement tasks. Fine. So yes, I think now you understood this third scenario. Now we'll go for fourth scenario. So low model latency is not required, or model can be run in an offline fashion. So systems that can be run on a batch process like retail product catalog analysis. Okay, so what is this retail product catalog analysis? So what happens is whenever a particular um, product category is being bought by the customers, we do some customer segmentation and then we analyze which category or catalog is most interesting for what kind of customers. So these kind of analysis happens. So for these kind of tasks, we need to collect data on a time period basis, like for a week. We'll take the data, what to say, store data for 1 week as a batch and then use that 1 week's data together for doing this analysis. For that kind of NLP systems that is specifically for analysis or that can be done even offline, for those kind of systems you can actually use a slower models also. Like it need not have some higher computation or super architecture or something, but then it can be advanced. You can may even see some even advanced models take time, but then if you want even compute advanced model very fast, you will have to have a bigger computing power, right? So here in this case, you can use the advanced models because there'll be no need for low latency. So this can actually help you in even optimizing cost where feasible. So usually for computing you need money, right? So for bigger computing you need money. So even with smaller computing power, you can actually run advanced models. So we because we don't we time is not a big issue for us. Like latency is not a big issue for us here. So we can use an advanced model with lower computing power in this case for getting us the best result, and also saving us cost, and also doing this analysis for this particular NLP system. There could be many other cases where this particular scenario and this particular decision can be applied, right? So these are the four different scenarios and the decision paths which we can take. So I hope you understood the intuition and the whole uh, thinking pattern for how we come up with solutions for different challenges here, for different scenarios here. Find all of the four scenarios. So this is the whole deployment phase. I hope you understood the industry's mindset also. So yes, with this we wrap up the whole NLP pipeline lecture, second part. After this, we'll be looking into a real-time case study of Uber. Fine. So see you in the next lecture then. Bye.